Back. So we were continuing to look at square root of x plus 3. Its approximation, that is the linear approximation, is 7 over 4 plus x over 4. Okay, now the question is, suppose I am willing to accept only 0.5 as the difference in the actual values and the approximation. So here to here is probably acceptable and so on. But I don't want to go from, say, 2.5, the actual value being, I don't know, 3, and this being 3.6. So we don't want such a big margin of error. We are allowed only 0.5 margin of error. That means the difference between the actual value and the approximation. So difference, remember, you could be more or less. Therefore, you take absolute value. The difference is allowed to be less than 0.5. So what does that mean? If I open this up, it means the square root function minus 0.5 is less than the approximation, which is less than square root plus root 0.5. That is, this is the actual value, and my approximation is allowed to go a little off on the left and a little off on the right, but it should stay within that range. That is, the linear approximation should lie between the curves obtained by shifting the curve upward and downward by just that much allowed. So you see, so that is my original curve, and that is the tangent. I'm allowed to move my tangent. I'm wanting to make sure my tangent stays within a small shift above and a small shift below. So if you notice, there are these intersection points of the line, tangent line, with the shifted curve. Beyond that, the tangent line goes way above. So we want to stay between P and Q. In other words, you want to find the x coordinate for Q, x coordinate for P. In that interval, the tangent line is within the acceptable margin of error. Okay, and that's how you zoom in, use technology, and find the coordinates of P. That's what they have done. Coordinates for P, x coordinate for P, and x coordinate for Q. Between these numbers, my approximation is well accurate within 0.5. All right. So that's all. So that's how you can use technology to figure out an entire interval where this tangent line approximation is good enough. Now, here we start applications. Linear approximations are often used in physics. In analyzing the consequences of an equation, a physicist sometimes needs to simplify a function by replacing it with its linear approximation. For instance, in deriving a formula for the period of a pendulum, physics textbooks obtain the expression at equals negative g sine theta for tangential acceleration and replace sine theta by theta. Sine theta is very close to theta, okay, if theta is not too large. Sine x is very close to x if x is not very large. Okay. Okay. All right. So you may replace sine x by x as long as you are within the range, acceptable range. Likewise, you can replace cosine by 1 by its linear approximation if theta is close to 0. Okay. Now for differentials, the ideas behind linear approximations are sometimes formulated in the terminology and notation of differentials. Okay, what are differentials? If y is fx, where f is differentiable function, then the differential dx is an independent variable. that is dx can be given the value of any given number, the differential dy is given by this formula. Dy is derivative at x times that number you give dx to. Alright. So dy is a dependent variable. It depends on the values of x and dx. If dx is given a specific value and x is taken to be some specific number, then the numerical value of dy can be determined. So you see, you need to tell me what x is, you need to tell me what dx you are choosing. Then you can calculate dy using this formula. That's all they are saying. Okay, so dx is typically delta x, that is difference in two x values. Delta y is difference in two y values, you see. But dy is basically the difference in the y values of the tangent. All right. So when you're close enough to the curve, dy is very close to delta y. That's the point of it. Okay. If p x fx and q x plus delta x f of x plus delta x are the points on the graph of f, let dx be delta x. Then the corresponding change in y is delta y. What is the corresponding change in y? You are using the actual f. Whereas when you use the slope, that is f prime, you get dy. Okay. So dy is usually very close to delta y as long as delta x is very small. Okay. So we'll come to the next example in our next video. Until then.